So a very good morning. Assalamualaikum and a very good day to everyone. Okay. Sorry for the delay. I have something that I have to handle before we start for today's session. Okay. I've already shared the attendance link. Okay. And also you can scan the QR code from the screen that I've already shared. Okay. And then there's a question, Abdul Kafi. So are we going to have a quiz for today? Yes, the answer is yes, because I've already announced earlier and also announced that within this week. Okay, so yes, we will have it later today. At the end of the class, it's my discretion when I want to do it. Okay, so perhaps I will stop at half an hour after this and I'll start the quiz. That's my discretion. Right, so just be here, and when I announce the quiz start, then you'll be able to answer the quiz. Okay, just be ready. All right, so for today's session, we will like to cover chapter 10, which I have missed to cover that for these few weeks. Okay, so in chapter 10, basically, what happened to my screen? Okay, so I hope that you guys can see this, right? Since my screen, I won't be able to see the chat. Okay, so if you have any question, please turn on the voice, okay, or turn on your mic and please ask the question verbally, right? So for today, we will have the discussion on network layer, okay, delivery, forwarding, and routing. So basically, this is the continuity to the network layer, IP addressing, and so forth. Okay, so now we will look into how the packet is being delivered, especially on the routing purpose lah. So basically, if you have a router, then you need to do some routing setting so that you're able to route the packet to the specific network that you want to be connected to, right? So this the purpose of today's session: understand packet forwarding techniques and the process. Describe how network determine routing table using static and dynamic protocols. So this, when we talk about routing, basically each and every devices, okay, that perform this transaction will need to have a routing table. Your device itself will need to identify your network. Okay, so that is basically how do you want to get to the other network. Okay, and when we look into packet tracer last time, when we do switching, one of the main thing that we mentioned is that we need to define what is the default gateway. Okay, so basically, if you want to get to the other network, which the network is not being physically connected, okay, so all the physical connected we identified with respect to the switch or the router itself. But other than that, we need to do some setting, okay, either default routing, static routing, or perhaps automatic routing. Okay, so with respect to that, they will know how to get towards that. Okay, and one of in IPv4, I've already mentioned that we need to identify what is the default gateway. Okay, and then differentiate between routing protocols, the distance vector, link state, and also path vector. Okay, basically, there are two main methods that we can see in how the router able to get the routing information. Basically, there are two ways. The first one is that they get it from the neighboring router. Okay, so they will able to get that information from the direct neighbors. Okay, and they will try to update the routing table based on what information that they receive from the neighboring router itself. Okay, the other one, which will based on the router will have all the information about the routing. Okay, so we will see that what we call distance vector, which is actually the one that updating from the nearest neighbor. Okay, and the link state. Okay, which actually based on full routing information. Okay, so there are two different methods lah, and with respect to that, there are a few different advantage and disadvantage. Okay. So we will look into this direct and indirect delivery. Okay, so direct basically when you are attached physically. Okay, so you are connect directly. But then if you are in different network, which means that you have to go through several switches, okay, or several routers. Okay, so that is where we will define this an indirect delivery. Okay, and then we will also do forwarding techniques, process and routing table. Okay. And last but not least, unicast routing protocol. Basically, we will look into the different types of protocol with respect to the routing. To name some of it, like RIP, you have the OSPF and also border gateway, BG. Okay, so these are the few common routing protocols that being used. Okay, and with this unicast routing protocol, it also can be separated into two types. One is what we call intra-domain routing, meaning that they are actually performing the routing within the autonomous system. Okay, we also define what is autonomous system. And then the inter-domain routing, basically this is if you are not having the network itself. Okay, so you are sharing between a few ISP, internet service provider, for instance, Celcom, DG, and so forth. Okay, so what you will be able to interconnect between all the different ISP is through inter-domain routing. And with inter-domain routing, basically, the main factor of this is to make sure that you have some what they call it management lah. Okay, on the management level of that ISP. For instance, you don't want the packet to be route more going outside from your own switches. Okay, so perhaps you have that option to be connected to others through your own routing switches and routers. Okay, so if possible, you don't want it to go direct to the other ISP. Okay. Okay, so that are the things that we will look into for today. Okay. Okay, so on network layer, okay, basically we are trying to send it based on packet by packet, right? So we define that in the network layer. Okay, so the network layer supervise the handling of the packet by the underlying physical network. Okay, so whatever the networks behind that, okay, so it has to process, okay, because in physical layer and data link layer, it means the process is from bit by bit, okay, and then for the network layer, it will process between host to host. Okay, so you need to identify. So you will see that the header of your network layer basically can change based on the IP address. Okay, so it needs to give different IP address on the header when it move from one intermediate switch to another intermediate switch. Okay, so we have to define the handling as the delivery of the packet. Okay, so as mentioned, there are two different definition. Okay, so the first one is what we call direct delivery and indirect delivery. Okay, so here it defined in a direct delivery, the final destination, it's just like a movie title. The final destination of the packet is a host connected to the same physical network as the sender. Okay, so this is what I did mention, that for a direct delivery, it means that you are attached to the same network physically. Okay, and if the host destination is not the same network as the sender, the packet is delivered indirectly. Okay, so basically, if the host all the host is being connected physically, then we can say that is a direct delivery lah. Okay. Other than that, is indirect. In an indirect delivery, the packet goes from router to router until it reaches the one connected to the physical network as its final destination. Okay. So these are the representation, the diagram that differentiate between direct delivery and indirect delivery. Okay. So for a direct delivery, as mentioned, it will actually have a same network, okay, meaning that physically connected through this network, okay. So that is why it says that is a direct delivery, okay. But also here between the routers, because this router is connected physically, okay, so it's a direct delivery, okay. Then from this router going out, okay, so it will be indirect lah, okay. So now we can have in the same diagram, okay, from host to the destination, source to destination, okay. So within this, between this PC to this router is a direct, between this router to this host is direct, but between this source to this destination is considered indirect delivery. Okay, so these are what you can see. Okay, meaning that if the packet is purposely for this router, then that will be a direct one. Okay, but if the packet is need to be sent out of the router, okay, so it's considered as indirect. Okay, so there's no confusion about this. Okay. Right. So what are the terms forwarding means? So forwarding means to place the packet into its route to its destination. Okay. So you just wanted to make sure that the packet is being delivered to the next destination. Okay. So the forwarding requires a host or router to have a routing table. Okay. It means that you need to refer to the routing table. What is the next hop, or perhaps you need to know what is the next stop, okay, for that packet itself. Okay, so when the host has a packet to send and when the router has received the packet to forward it, it looks at this table to find the route to the final destination. Okay, so in this temporary or intermediate devices, okay, perhaps it doesn't give you directly all the destination that it has to fall in. Okay, but the very basis is that it will define where to go next for that router to reach the end destination. That is where we say that what is the next hop. Okay, we don't define it to the end destination. If you have that information, you will have to end up with a very huge header, because you have to identify everything within the packet, okay, end to end. So you will need to have packet A have to go to packet B, C, D, E, F, and until G, then you will arrive at the receiver. We don't do that, okay? So we just inform, okay, this packet, this is the sender, the next hop, what is the IP address, and so forth, okay? So that is what it means by we have to deliver or we have to look into the routing table itself, because the routing table give you some information where to route. And in routing purpose, you will find what's the best path to the end user, okay, with so that it able to arrive that at a very faster speed. Okay. All right. So these are the different methods. Okay, the forwarding technique itself. The one that I've already mentioned. The very basis is the next hop. Okay. Versus method versus the route method. Okay. The next hop basically give you identification what would need, where it needs to go, so that it able to reach the end user. And the route method here means that the router itself know the whole network, okay, and it will give you the information with respect to the whole routing. Meaning here, okay, all the the routers will have the same information. Whereas for the next hop technique, basically we'll see that that specific router will have its own identification of the router, okay, or the routing table, whereas the other won't have the same thing. Okay, that is the difference lah. And then we can also see on the network specific method or host specific method. Here it means that you can give the routing based on the network specific. So that you want to go to network C, so you have to identify that the next hop or the routing will be based on the network itself. Okay, whereas a host specific means that you define the final as the host IP address itself. Okay, and then you have a default method, okay, which actually give you a blind routing, so that basically if you don't know where to give this packet to, okay, so by telling that, oh, if you don't know anything, just go to this specific switch or port itself, so that it enables to process your packet. Okay, so these are the few techniques that we will see later on today lah. Right. So this diagram, okay, or this figure 2, represent the route method versus the next hop method. Okay. So as you can see on the right hand side over here, it defines the next hop, and you can see that compared to this same information with respect to the route method. Okay. So the route itself, okay, it gives you the information where to go from host. You are from host A, okay. You want to go to host B, okay. So you are host A here. You want to go to host B. It defines all the interface, all the intermediate devices that it needs to go before reach host B. Okay. Compared to this next hop method, so it's just telling you, okay, if you want to go to host B, you ask R1. Okay, so the next hop is R1. So that's a simpler way to give direction. Okay, and then the packet will need to ask R1, and R1 will say that the next hop will be R2 and so forth. Okay, so this will actually give you a simpler version of your routing protocol, but it doesn't give you the whole idea of the hop that you need to reach lah. Okay, sometimes you don't need to know, you just want the direction. Say that for instance, in when you do or when you use Waze, okay, to find your destination, you just want to know from this from your point, okay, where is the next interchange, for instance. Okay, so this is the way lah. Okay, but the whole of the Waze itself is already giving you, okay, to get from point A to point B, these are the path that you are given. Okay, but compared to this next hop means that when you start to drive, okay, so what's next that you want to know is which are the next junction. Okay, in 300 meters, you have to turn right. In 400 meters, you have to turn left. Okay, that is how you can imagine, okay, the next hop compared to the route itself. Okay, so here you can see the routing table for host A, for instance. You are at host A, so you have the information. If you want to go to host B, then you have to go to R1, R2, and then host B. Okay. Then at the routing table of R1 itself over here, so when you have the packet and your destination is host B, then you will say that, okay, the next thing that you have to go is R2 and then host B. Okay, so that is what it defined over here. And on the routing table for R2, okay, if you want to go to host B, actually is connected here. Okay, so these are the whole information. Okay, but this is on a single network. But just imagine that you have multiple networks, multiple connection. Okay, so your routing table will be huge. Okay, this memory of your routing table basically during on perhaps few years ago, okay, because the device is not that powerful and have very limited storage, okay, it will be very troublesome because it needs to have much more memory capability. Okay, but perhaps right now, because of our devices having more memory, okay, so there's a possibility to implement this. But the point is that it will give you or it will use a lot of memory, with respect to if you have a lot of network that you need to configure or you need to identify. Okay, so compared to this, based on next hop, basically you just need to know what is the next destination. Okay, so at host B, if you want to go to host, if you are host A, you want to go to host B. Okay, you need to ask R1. Okay, then getting to R1, you want to go to host B. Okay, you have to ask R2. Okay, and then when you got to R2 and you want to go to host B, then actually you are already connected. Okay, so you have no problem. So these are the difference between a route method versus next hop method. Okay, so because this will be a very basis in our routing protocol later on, that you will see that this represent either a kind of a next hop or routed method itself. All right. Okay, and then it can also be defined as host specific versus the network specific method. Host specific, basically you want to go your destination. If for instance in N2 you have host A, you have B, you have host C, and you have host D, right? Okay, so your routing table can be based on this destination. So A, B, C, D. So the next hop is R1, 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 R1. Okay, because they are on from the same network. Okay, or you can base on network specific method, meaning that if you know that if you are in network 1, if you want to go any host in network 2, okay, the next hop is R1. Okay, so this is based on hop specific, okay, meaning that the destination itself is be defined either through host or through network. Okay, so that's the difference. With this method, basically, if you have a lot of devices in this N2 network, okay, so you will need to list every host within this. Compared to here, it's just mentioned that, okay, if you want to go to this PC with this IP address, okay, so why not you just go to this network and it will route you to the specific host. Okay, so that is the difference between host specific, okay, and also the network specific method, right? And then there's another method, is what we call default method. Okay, so if you have done your packet tracer routing in IP before, basically when we talk about the routing where you have 0, dot 0, dot 0, dot 0, okay, then slash 0 itself, okay. So this is actually the default route, okay, with a net mask of 0, 0, 0, 0 also, right? Okay, so in IPv4 also we tend to have this colon, okay, and then slash 0. Okay, so this is also default route. This is IPv6 itself. Okay, what does it mean? Okay, so it means that by this default route, if you want to get routing from any network that you don't know, okay, so you just go to the specific. Okay, meaning that here you just have one single point of if you want to imagine, just like what they call it, a counter that people ask you question, right? Okay, so this is where you have this default router. Okay, so here it will say that if you want to get to network 2, you have to go through router R1. Okay, but other than that, you have to go to router 2. Okay, so the rest of the internet. So if this kind of a lazy configuration lah. Okay, so you can say that if you have a lot of network on the rest or through R2, so you just need to define that, anything that you want to find any other than the network 2, just go to the R2 and it give you the resolution to the rest of the network. Okay, so that is what we call default method. Okay, so again, how you define this in your switching, okay, you can do the 0.0.0.0/0 or double colon /0 for your IPv6 itself. Okay, and then simplified for the module in the classless address. Okay, so in a basic routing table, you will have this routing table. Okay, so how does this routing table perform? So basically, when you have this packet being sent to the switch or device, okay, so on the forwarding module, it will try to extract the destination address, okay, and then it will put into the search table and it compare it with the routing table itself, okay, and then it will identify the next hop address and the interface number, okay. So this is where you have to actually get your ARP to match between the address and the interface number so that you're able to perform it, okay. So in your what they call it routing table, the first thing that you will look into the mask, okay, then what is the network address, the next hop address, and then the interface itself, okay. So these are the table that you can see, okay, so that you're able to perform the forwarding process, okay. So in a classless address, we need to at least have 4 columns in the routing table, which are the mask, okay, the network address, the next hop address, and also the interface, okay. All right. So these are few example, okay, and the example for me, I would say that it will be a bit confusing if you don't understand the routing table what they call it, information, okay. So basically in this few example, the first thing that it needs to look is on the mask, okay. If the mask is within the network, then it will identify the network address, okay. Then it will have to identify what is the next hop, and finally what is the interface, okay. So these are the reference for this example that we look into this, okay. So this also will be discussion will be respond to this diagram, okay. So in this diagram, basically you have 2 routers. One is router 1, and this other one will be we'll say router 2, like it doesn't list it down as router 2, but we can say that it's a router 2. All right. And out of this, okay, you will see that we have 4 different network, right? Okay. So you have network number 1, number 2, 3, 4, and actually there's another network over here, right? And you can see that this is the port, okay, that attached to this network. Okay, so for instance here, your network is 180.70.65.128/25, but the interface that it used is 180.70.65.135/25. Okay, so basically this is the network address, and this is the specific host or the specific port that being used to identify this, okay. And the interface over here is M0, okay. And then for interface M3 is connected to this network 22/0.0/24, but the specific interface is 22.3/24, right? And from here, it has 16.0/22 network, okay, but specific the IP address, okay, will be 16.2/22 with the interface of N1, okay, M1. And then here you have the network of 192/26, okay, and the specific IP address is 194.26, okay. Interface is M2. And the other interface over here that connected to the second router is this, and the next network will be here, but it's not defined with respect to this example itself, okay. So make a routing table. Okay, the example over here. Make a routing table for router 1 using the configuration in figure 6. Okay, so you are asked to make a routing table with respect to this example figure 6 itself. Okay, so you will need to have at least 5. Okay, for instance, if you wanted to have the rest of the network, okay, in your table, you tend to get information that anything other than this network need to be go through this router 2, okay, with respect to this interface 265.200/26, okay, and the rest you need to configure lah. So anything that within this network, okay, it needs to go through this interface M1, anything to pass through 65.125, through M0 and so forth. Okay, so you need to have this table to represent your in your routing table. Okay, so the first thing is that you have to have your mask, okay, and then the network address, next hop, and the interface, right? So as mentioned, okay, so you need to have at least 4, and the rest will be needs to go through the this interface. Okay, so here any mask, any network, okay, and then the next hop would be 65.200. Okay, so this is where you need to go if you have any other than the 4 network that been defined on the routing table. Okay, so the rest will be as follows. Okay, 65.192 with M2. Okay, so this is with M2 65.200. Okay, 65.192. Okay, 65.192. You need to go through this M2 and so forth. Okay, so these are the routing tables. So now you can see that the mask is being aligned over here, the network is being aligned over here, then the next hop and the interface. Okay, so with that information, you will see that the following example will also follow this lah. So the first thing that it needs to identify what is the mask. Okay, if it's aligned with the specific mask, then you can see on the network. Okay, so here you can this example you have the mask 26, mask 25, mask 24, and mask 22. Okay, so after you have compared that, if any of that is within this specific mask, okay, so now you can see that you can have the network address attached to it. It's so that you need to deliver it through this interface. Anything else need to go through this interface with respect to M2. Okay, so that is what it be defined, right? So this example 2 also will follow the exact example that we have. Okay, so here it says that show that the forwarding process if a packet arrived at R1 in figure 6 with the destination of 180.70.65.140. Okay, so if you look at this, okay, so you can see that it start asking about the mask. Okay, so the router performed the following step. The first mask 26 is applied to the destination address, and the result is 180.80.65.128, which does not match the corresponding network address because this is with slash 128 itself. Okay, and with respect to this IP address, okay, so this doesn't match with this. Okay, so it doesn't match with the slash 26. Okay, so it will move to the next one. Okay, it will actually discover the second mask. Okay, it apply to destination address. The result is still 128.65.128, but with matches the corresponding address. So the next hop address of the interface M0 are passed to ARP for further processing. Okay, so it will actually 140. You need to identify which are the next mask. Okay, so basically if you have this slash 26, okay, so you will need to have additional 2 bits to be used so as your mask. Okay, but if you look into it, the 192 will not match to the IP address that been given, whereas the 25 will actually match with the given one. So that is why it will use the IP network 65.128. Okay, and then a next example is that if you have 204, 22, 35, okay, again, the first thing is that it needs to go to the mask, okay. So the first mask from here, it says it doesn't match. The second mask doesn't match. The third mask is matching. So with respect to that, it says that you will see that the result is 201.4.22.0 with match to the corresponding network address, and the destination address interface is M3. Okay, so again, I will say that if you read this description in this slide, you a bit confusing. Okay, but if you able to understand with respect to this table, okay, and you know how the mask working, okay, so you have to refer back how do you identify the mask with the specific network address, so you can understand it further. Okay, but in this description itself, it mentioned that it doesn't match. Okay, all the first different masking, and then only the third mask is will be matching. So that is where you can see that it will process and the packet will be passed to the M3 itself. Okay, and same goes for the last example. Okay, so these are the rest of the address which network is not within the one that been given to us. Okay, so this time all masks are applied one by one to the destination address, but not matching network address is found. So when it reached the end of the table, the module give the next hop 180.70.65.200 and interface of M2 to ARP. So this is probably an outgoing package that needs to be sent by a default router to someplace else in the internet. Okay, so again, this with respect to the IP address. Okay, so if you're able to comprehend how does the where we define that for instance over here, what 65 over here. Okay, so this is /25. Basically, it used to or it can divide it into two different what do you call it, address submask, okay, subnet, which it goes from 00 to 127. Okay, the next network is 128. Okay, so anything within that it should be within that network. Okay, or if you here is between 128 to 255 itself. Okay, so these are the network, and this one, okay, perhaps is within the region of 192 until 256. Okay, so these are two different method that you can see. Okay, so based on the IP addressing. Okay, but if you able to identify it based on the network addressing or network mask, then you'll be able to understand further. Okay, but these are with respect to the example that being given. All right. Okay, so that is on the basis of routing. Okay, so now we want to take a look into the different algorithm or dynamic routing tables. Okay, so by this dynamic routing table, it means that it can be updated based on any changes of the network, right? Basically, on the default routing, you do that as a static configuration. Okay, and then you can also have a static routing, which actually it can be configured manually, but basically if any changes need to be done, okay, so you also need to change it manually. Okay, but say that you what they call it, the network is very large. Okay, and you unable to actually do changes abruptly if any change in the routing what they call it system, or the routing have changed due to some problem, say that one of the network down and so forth. Okay, so you cannot rely on manual configuration. You cannot rely on default routing itself, because default routing basically it gives you just a blank routing, okay, which sometimes you just wanted to make sure that only specific user can go to this specific routers or so forth, okay. So you cannot give blank, you cannot do abrupt changes, so that you need to have this what they call it, dynamic protocol routing, okay. So a host or router has a routing table with entry of each destination or combination of destination to the IP route, and the routing table can either be static or dynamic, okay. So is static, it will define as, for instance, in when you do packet tracer, so it's a static one. A dynamic, it will define either you use the RIP, where you use the initial of R, OSPF 0, BGP, OSPF O, BGP is B, for instance, okay. So for a static routing table, it contains information entered manually. Okay, so you can manage it manually, but if you are unable to do changes, anything that need to be updated as soon as possible, then you'll be doomed lah. Okay, so the table cannot be updated automatically when there's changes in the internet. It is used in a small or in an experimental network. Okay, so usually if it's a small network, even MMU is considered big, okay, and you are unable to do that manually, okay. So the option that you need to do is that using a dynamic routing table, okay. So it is updated periodically using one of the dynamic protocols such as RIP, routing initiation protocol, and OSPF, okay, or BGP, right? So these are to name few of the dynamic routing protocol. Okay, so in a common routing table, so these are some of the field other than the mask, the network address, net hop address interface. You need also to have flags and also reference count and use. Okay, so these are additional information perhaps that need to be added to your routing table itself. Okay. Okay. And then routing table, okay, as mentioned, can be either static or dynamic. Okay. A static table is one with manual entry. A dynamic table is one that is updated automatically and when there's a change somewhere in the internet. Okay. And a routing protocol is a combination of rules and procedure that let routers in the internet inform each other of changes. Okay, so basically the routers, when you are using it, okay, for instance, in your lab itself, you can see that sometimes the router has not it doesn't finish doing the exchange of information. Okay, so that is where you can see the orange indication in your packet tracer. When it's already fully developed or fully understand the whole or the whole process have done properly, then it will turn green. Okay, so then you will able to actually see that what the implementation that you want to do actually have been successfully being done. Okay, so there's some rules or procedure, and also it takes a bit of time to do that. Okay, and then if there's any changes, then it's need to have some period of time also to do the changes itself. Okay. Okay. So with the routing, okay, there are two different types. Okay, intra and inter. Okay, and as I mentioned that there's a term that is called autonomous system. Okay, so in this term autonomous, it means that if you have a group of a network and you are the owner of that network, okay, so you are saying that you are having a single autonomous system. Okay, so you are having one autonomous system or a single autonomous system where you have a single authority or a single administration. Okay, so one autonomous system is basically one network that being governed by a single admin. Okay, so here it mentioned an autonomous system. Okay, so this is the definition: is a group of network and routers under the authority of a single administration. Okay, so it can have switches and routers that perform the network function, okay, and it is being managed by a single administration, and that is called the autonomous system. Okay, so the autonomous system can also have two different locations, but still you are within the same network. Then it's considered as one autonomous system if you want to define it, or perhaps you can say that you have two different autonomous system. Okay, but you have the same admin. Okay, so whatever the definition you want to have lah. Okay, and the routing inside the autonomous system is referred as the intra-domain routing. Okay, so define this intra-domain routing. If you are managing inside the network, inside intra, then routing between autonomous system is referred as the inter-domain routing. Okay, so if you our network, say for MMU, okay, we have one autonomous system in MMU. Then since you want to exchange information perhaps with the other university, okay, that close to us, okay, and it being connected physically, okay. So what you can do is that you can have this router that talk between each other, and there is only one router that interchange information between one autonomous system and the other autonomous system, or it can be much more, but the basic one is that it can communicate between one autonomous system inter-domain router to another autonomous system inter-domain router also. Okay, so you have to identify lah, or you have to remember, intra is inside, inter, okay, is between. Okay, when you have Inter Milan, for instance, to remember, Inter Milan, okay, they are fighting in between. Okay, so perhaps you can remember that. So inter is between, then intra is inside the autonomous system. Okay, and each autonomous system can choose one or more intra-domain protocol to handle routing inside the autonomous system. Okay, so you can choose either RIP or OSPF or other types of intra-domain protocol. However, only one inter-domain protocol handles routing between the autonomous system. Okay, so for the inter-domain, okay, so you need to have only one type of protocol with respect to that. Okay, so in this diagram, we have four autonomous systems. One autonomous system is perhaps managed by a single admin. Okay, so you have four, and there are few routers, okay, and a few specific hosts. Okay, so here you can see that perhaps this is a switch that connected to router 2. So R1 can be connected to router 2. So in between here, okay, so perhaps you need to have from intra to inter. Okay, inter. Okay, so here is inter and here inter. Okay, within that is intra. Okay. Right. So for intra-domain, okay, so you have a few others. Okay, you have RIP, OSPF, and some other protocols that perhaps did not mention over here. Also, you have this inter-domain with respect to this BGP, Border Gateway Protocol. And with respect to that, these are the algorithm that being used to define these two different types of domain. Okay, so intra-domain, it use distance vector. We'll look into this. A link state also will look into that, and a path vector that also will look into that later on. Okay, so with RIP using distance vector, so a distance vector routing. Okay, so what is this distance vector routing? That will be the main question that perhaps you wanted to know. Okay, so in a distance vector routing, a least cost route between any two nodes is the route with the minimum distance. And in this protocol, each node maintain a table contain a minimum distance to every other node. Okay, and the table at each node also guide packets to the desired node by showing the next stop in the route. Okay, so basically distance vector. The term here, maybe you can remember, distance means that it's a very touchable distance. Okay, or a very close distance, and here means that the information is being given, or you can have the information from the closest neighbors lah. Okay, so the one that being attached directly is the one is called the closest neighbor. Okay, and information can be updated from the closest neighbor, and actually the information is where it can say that you can actually use if you have any packet to be delivered. Okay, so it will represent this is the next hop. Okay, so that is the distance vector routing table. But it also have some other information like what is the best path towards it. Okay, so it has the least cost route between the nodes. Okay, so these are example of the least cost table of distance vector. You can see that it will give you an option, okay, to where about that you can go with the best cost or the least cost with the smaller or the shortest path or the smallest time that you want to go from one end to the other end. So here you will define a host by host connection. Okay, so you are from A, okay. And if you want to go to A, meaning that this is the actual one, so cost is 0. So this is the its own switch, okay. So its own router, so the cost is 0, okay. Don't need to go to the next hop lah, okay. And then B, okay. For if you want to go to B, you have two options, okay, 5 and through C, okay. But the cost will be much lesser using direct from A to B. Okay, so you identified that B will be having the best route directly lah. Okay, then also go to C. Okay, you can go through B, but the least cost will be directly through C. Then for D, okay, going from here to D, there's only one option directly, and the cost is 3, and there's no next hop. Okay, and if you want to go to E, you have option. Okay, so you can go through A, B, C, E. You can go through A, C, E, and you can go A, B, C. So you have to choose based on the least cost, and it says that if you want to go to E, the least cost will need to go to C with a cost of 6. Okay, and you can also look at different tables. But say that if you want to look at this table D, routing table for D itself. Okay, so going to A, direct one. Okay, but the rest. Okay, so you can see that going from to B, C, and E with a different cost. However, you need to go to A. Okay, so means that here from D you have to go to A, so that you can reach B, you can reach C, and you can also reach E. Okay. Whereas for E, for instance, over here, okay, perhaps okay you can go to B and C. Okay, B and C is a direct connection, and then going to A again, you need to pass through C. Okay, and going to B, okay, or going to D itself, okay, again you have to pass through C. Okay, so these are the different information that being surrounding by the routing table. Okay, and again you can see that with a distance vector, all the routing table is different between one and each and any of the routing table in each of the router itself. Okay, it doesn't have the same information. Okay, so this will also be compared to a different techniques for the routing table, which is actually we will define it as the link state itself. Okay, all right. The next diagram actually is to show how that this routing table converge. Okay, so it initially will have this information. Okay, because it will only know where to route with respect to the next network or the next router that it has. Okay, so basically for router A, say here, it's directly attached to D, B, C, and D. So it already know all the information with respect to A, B, C, and D. except for E. So that is why it says that the cost is infinity because it doesn't know yet what will be the cost there. Okay, so you will have the initial table as such. Okay, same goes for the rest, like this D. Okay, so it only attached to A, so it only knows that the cost to A, the rest is being infinity. Okay, so this is the initial table itself. Okay, and in distant vector routing, each node share its routing table with its immediate neighbors periodically, and then when there is a change. Okay, so the neighbors, okay, immediate neighbors, meaning that as mentioned, okay, so like A, information can only be received from D, C, and B. It cannot get any information from E because it's not being directly attached. Okay, so immediate neighbors, that is what we call immediate neighbors. Like C, you unable to get any information for C, B, and E because it's not being connect directly. So anything that needs to get its information is from A. So later on, okay, the information that how to reach the rest of the router, okay, basically is come from A. Okay, so it will get this information from A directly to B. Okay. So when a node receives two column table from a neighbor, it needs to update its routing table. Updating takes 3 steps. Okay, so the 3 steps where the first is to receive node being modified. Okay, and the receive table by adding the cost between itself and the sending node to the each value in the second column of the receive table. The next one is the name of the sending node is added to each row of the receive table as the third column. Okay. And the receiving node compare each row of its old table to the corresponding row of the modified version and receive table and choose the row with the smallest cost. Okay, so it needs to compare it with the information that it received from the neighboring node. Okay, so for instance here, receive from C. Okay, so here you are in A, okay, so you receive from C, you are from A, okay, you are at A, you get information from C, okay, where this is the information, then A will modify the table, okay, where it needs to include the next hop is actually C, okay, and then this is the old A table, it will compare the cost lah, okay, between A to A, the next or the least cost is 0. Okay, so that is why it gives 0 over here. Then it compare between B, 5 and 6. Okay, if you go through B, then is directly, so maintains the table with 5. Then it compare between C, both are 2, but this one is direct, so it's actually maintained. Then D here, it doesn't have information beforehand. Now you will receive or basically it has the information and D doesn't know that. Okay, so now it can update the table as or it maintain the 3 over here. The E itself lah. Okay, it doesn't know where to get to E. So now you will get the information that going to E, it has to pass through C, and this cost will be C. Okay, so now the only information that be update here is E. Okay, because it doesn't know where to go to E. Okay, so this is where you can see the it's being updated lah. Right, so that is using distant vector lah. Sorry, there's some more. A problem with distant vector routing, okay, this is the problem, is instability, which means that a network using this protocol can become unstable. In this example, with 2 nodes shown in figure 13, the cost of reaching S increase gradually until it reaches infinity. At this moment, both A and B knows that X cannot be reached. However, during this time, the system is not stable. Okay, so this diagram give you the where the routing table give or is unstable within this, okay, because there's beforehand there's a network X, okay, before the failure, okay, but now if it has a failure, then it can see that it's not getting the update or it will give you instability of your routing table. Okay, so that is one of disadvantage of using distant vector. Okay. Then the other routing table that we already used beforehand, okay, is called the Routing Information Protocol, okay, RIP, shortly known. So RIP is intra-domain protocol used in the AS, and it's a very simple protocol based on distant vector routing. Okay, so it's still using the distant vector routing. Okay, RIP implement distant vector with some consideration. Okay, as in an AS, the router have a routing table. Networks do not. Okay. And the destination in the routing table is a network, which means that the first column define the network address. Okay, so now it define rather than host to host, it define the network address. Okay, so the metric in a RIP is called a hop count. Okay, instead of the cost is a hop count. Okay, so how many hop that it needs to get to the next or to the end user. And infinity is defined as 16, means that it can only goes up to 16 hop. Okay, and any hop using RP cannot have more than 15 hops altogether. And the next node column define the address of the router to which the packet is to be sent to reach the destination. So now it use the network address rather than the host address, right? So here is the network address, okay? And then you have what it will be the hop, and then what is the next address, okay? So this is RIP. So here you can see that you have few network, okay? So you have network 1, okay? Then you have network 2, then you have network, this is 1, 2, 3, 4, 5 altogether. 1, 2, 3, 4, 5, 6, 7, or 7 altogether. Okay. But the routing table is we'll see on the router itself. Okay. So say that your destination over here is 130, okay, .10.0.0. So you are trying to go to 130.10 here. Okay. So you are in router here, so then how many hops that you have to pass through is only 1. Okay, so you need to update here. What is the next hop between here to the network itself? It doesn't have lah, okay, because it's directly connected. Okay, and then 130.11.0.0, so it will have to go through this R1. Okay, but you have to pass through this network IP address. Okay, the gateway basically is 130.10.0.2. Okay, so the next hop will be this interface to the route inbound of your router 1. Okay, to get to this network. Okay, and then 195.2.4.0 and 195.2.5.0. Okay, here. Okay, so it's this going directly here, so that is why only 1 hop, and there's no next hop or next IP address. Same goes for 5.0. Okay, 5.0, 4.0 is up here, 5.0 down here. 6.0, okay, 6.0 is over here, so the next will be here. Okay, 192.2.5.2. Okay, going to 55.0, 55.0, you have to pass again through this interface. Okay, but then you need to count what is the hop. 1, 2. Okay, so you have 2, 3 actually. 1, 2, 3. Okay, 2, 3 over here. Okay, and goes to 60. 1, 2, and 3 over here. Okay, so 3 hop. Okay, so that is why you have this routing table. Okay, and again, for this address, you will see that it will have different information compared to the one that you have in R2. So this distant vector, and it can be updated between the neighboring routing. Okay. And then you have another type of protocol we call link state. Okay, so in a link state routing, each node has the entire network. Okay, so this is where it mentioned that you have the whole information of the routing for each and every of your router. Okay, so it has the entire topology of the domain, the list of nodes and link, how they are connected, including the type, cost metric, and condition of the link, up or down. Okay, and this node uses what we call Dijkstra algorithm. Okay, so what I've also been informed is that Dijkstra algorithm also being used in your ways how to calculate the best route to the end destination for your mapping in ways, okay, application. Okay, so you use Dijkstra algorithm to compute the shortest path to every other node, and this build its routing table. Okay, so this blind routing table, it represents that and it use this kind of topology. It's not being updated as this topology. It will be updated based on the next hop cost and the IP addresses. Okay, but what this diagram represent is that for node A or router A, basically it knows the whole network. Okay, and node D, it also have the same information of the whole network, and with respect to that, you have the same network for C, B, and also E. It doesn't change. Okay, with the distance vector just now, you can see that router A has different routing table compared to D, compared to C, B, and E. But here you can see that everyone on this network, they have the same information, not just the same information, but it has the whole network information. Okay, although here it seems that this one is much better than the previous one, but again, I just wanted to highlight that if this is the case of the network, you will have only 1, 2, 3, 4, 5 entries. Okay, but if you have a bigger and much larger network, then your routing table will be very large compared to this one. Okay, so in one way, it's not that practical to have this. Okay, but this can perhaps be implemented to certain type of network. Okay, but not the whole size of the network. Okay, right. So the link state, okay, is where you can see that A states of link, okay, B state of link, and it has the information with respect to the knowledge itself. Okay, so it will have all the information. Okay, so in link state, the routing table of each node is created using the following steps. So these are the steps that being used to get this routing table works. Okay, creation of the link state packet by each node, which contain information about the neighboring nodes and the metric of each neighboring node. Okay, so it will get the information from all each neighboring node. Okay, and then send this packet to all the routers. This action is called flooding. Okay, so it will or in IPv4 basically is broadcast to every switches that it has. Okay, or in IPv6 basically what we can say is that it will multicast it to the routers itself. Okay, only to the routers. So it has what we call multicast router, and computing the shortest path to each node using the Dijkstra algorithm. Okay, calculate the routing table based on the shortest path tree. Okay, so these are to identify from all the information that it has to compare, and it has to come to the end that it needs to identify what's the shortest path of the routing. And a tree is a graph of nodes and link. One node is called the root, and the other nodes can be reached from the root through only one single route. Okay, so we will see that we have done this, right? Okay, basically we have done this in when we talk about STP, right? The where you have to identify one router as the root and the rest as the other than root. Okay, so it's actually based on this Dijkstra algorithm. So you will have the STP being implemented in this algorithm. Okay, So you have the shortest path tree, is a tree in which the path between the root and other root is the shortest. Then what we need of each node is the shortest path, okay? And then create the shortest path tree from the graph. The algorithm divides the node into two sets, tentative and permanent. It finds the neighbor of the current node, makes the tentative, examine them, and pass. If they pass the criteria, make them permanent. And you can see that in this next figure. Okay, so these are the steps that being mentioned just now. Okay, and then basically it will form this tree, okay, and similar to the STP that we've already discussed in different chapter. Okay, and eventually you will end up with this permanent type of network. Okay, and with respect to that, you now have a single network, routing network that perhaps can be shared throughout the network, so everyone will have the same routing information. Okay, and then the next idea is that for this intra-domain, okay, rather than RIP, you can use this open shortest path first protocol. Okay, so this is an inter-domain routing protocol based on the link state routing. Okay, and the domain is also an autonomous system. To handle routing efficiency, OSPF divides the autonomous system into areas. The areas is a collection network, hosts and routers all contained within an autonomous system. An autonomous system can be divided into many different areas, and all network inside area must be connected. Okay, so here in OSPF, okay, it defines the network and also perhaps it defines the backbone. Okay, so you have this autonomous system, but in OSPF is again it separate into small area. Basically, it can have the network itself, okay, configuration, but as a backbone, you'll have one single area so that it can perform much more efficient, okay, because usually for backbone, you have higher bandwidth compared getting to the specific area of your network. Okay, so this is OSPF. Okay, then area border router are the router located at the border of area. Okay, so area border router here. Okay, and backbone router, all the areas inside the autonomous system must be connected to a backbone area, and the router inside the backbone are called backbone router. Okay, so these are the backbone routers. Okay, and virtual link, if the connection between the backbone and the area is broken, a virtual link between the router is created by an administrator. Okay, so this can also be supported through this virtual link, especially. Okay, so with respect to that, we already seen some example between intra-domain and inter-domain. Okay, so for the inter-domain, shortly known as IGP, and the inter-domain, shortly known as EGP. Okay, so intra-domain, okay, IGP, interior gateway routing protocol. Okay, for instance, you have the ISIS, okay, OSPF and RIP. Okay, we didn't mention about this ISIS. We already mentioned about OSPF and RIP. But this IGP or intra-domain definition is that routing within the same network. Okay, main issues is connectivity and the shortest path, because we want to have an efficiency within this network. Okay, and the routing inside a particular autonomous system. Okay, but going from your intra-domain to inter-domain, so here you define EGP, exterior gateway routing protocol. For instance, you use BGP, border gateway protocol. So its main function is routing between big networks, and example TM to perhaps Celcom or some other ISP. Okay, issues are money, policy, security, fair, traffic exchange, because within the network you want to save money rather than your packet being routed to different organization. Okay, so perhaps you want to keep within that network itself. Okay, so you will need to have these issues. Okay, and the network is grouped as autonomous system number. Okay, run in the core internet background, and BGP is used when you have two different views of internet. Okay, so these are the different. So here, much more on efficiency. This is much more on management. How you want to make sure that basically your packet doesn't go much towards other ISP, if possible, to your own network itself. Okay, and this border gateway protocol is the EGP or the inter-domain. Okay, for inter-domain protocol, you use path vector routing. Okay, and for the BGP session, the exchange of routing information between two routers using BGP can take place in a session. A connection that is established between two BGP routers only for the sake of exchange routing information. Okay, and BGP can have two types of session: external BGP and internal BGP. Okay, what is external, used to exchange information between two speakers node, belongs to two different AS. Okay, and inter BGP used to exchange information between two routers inside an autonomous system. Okay, so you can have these two different type of BGP itself. Okay, so with respect to that, what we have covered for today's session is basically we have defined what's the difference between direct and indirect delivery. So for a direct delivery, we mentioned that the network is being connected physically. Okay, so we call that a direct delivery. If it needs to pass through any intermediate nodes, okay, it what we call indirect delivery. Okay, then we saw how this forwarding techniques, okay, and the process, okay, and in details we see the routing table, okay, and with this routing table you can see that it can be updated either using your network, your host, okay, for instance, okay, and within that routing table, okay, you have this different intra-domain routing or inter-domain routing. Okay, so we define RIP, we define OSPF for the intra-domain routing. Okay, where we see that you can use either distant vector, which with distant vector, we see that the information is different for each and every routers. But with this, basically the information is not that huge. Okay, whereas if you wanted to have the whole network and have the same information with all these routers, okay, you can use link state routing. Okay, and perhaps if you want to use this interdomain routing, path vector with border gateway can be also performed, where for interdomain, basically the focus will be based on the management, okay, so that you're able to portray, or you want to make sure that all the information or the packet being exchanged within your own network rather than going to the other ISP. Okay, so with that, I would like to open to any question if you have, or you want to anything that you want to identify or to make sure that you are clear. You can ask the question now. Any question? Are you guys still with me? Now I have 98 all in total. Yes, Amadela, what is your question? Any question, Amadela? Or the rest? Do you have any other question? No question. Next week is the last lecture. Nope, we have another 2 weeks of lecture. Except that we have only one session, or next week will be the last session for the lab. When will test one be released? As mentioned many times, I'm struggling with the marking, but I hope that we will release before the end of the trimester with the whole mark. Okay. Sir, I'm not in a group of for assignment. I am from T7L. For assignment, it will be based on your lecture group. Okay, so if you are from the other lecture group, okay, so perhaps you need to group yourself with the rest of the lecture group. When can you explain the assignment question? I think the assignment question is clear, right? I don't need to explain it. Zaman, if you are from TC to L, my lecture group, basically I've already give you the link of all the student names that already been grouped and those who are doesn't have any group yet. Okay, so please check that link to the Excel sheet, and you can approach your friend. Okay, any of them, okay, so that you'll be able to be part of the group. I can see that few of the groups only have 3%. Okay, so perhaps you can join those who already have group but only have 3% in the group, because maximum is 4. Okay, and you're not allowed to have a single person for this assignment, and you'll be penalized if you do that as a single person. At least you have another students, okay, at least 2% will become a group. That one is acceptable. Okay, so Zaman, to answer your question, basically you have to go and find which students are actually not being assigned. Okay, if you want me to assign, you need to actually uh, basically email me, and I try to uh, assign those who doesn't have any group. Okay. By the way, if by today or by maybe by next week lah, Monday, if you still don't have any group, I will actually what they call it, force you to into some groups. Okay. There, Zaman, Muhammad Zahin already asked you to email him or email him so that you'll be able to be attached to that group. Okay. Any other question? Any further question? If not, I'll wanted to go to quiz 4. Okay. So you need to be ready for your quiz 4. Okay, so perhaps we do the quiz 4, and then if you have any other question, okay, you can ask me after the quiz itself. Okay, so I've already posted the link at Google Classroom, and also here would be the link for it. Okay, so we are currently 11:45. You have 10 minutes to answer all the questions. So now you can start with the question, and we'll end at 11:55. Okay.
Yeah.
Yeah. Just a minute. I will try to make it active. All right. So 11:46. So now I make the question active. Okay. And you can answer that within 10 minutes. Sorry, this is question quiz 4. Question 4, quiz 4. Okay, so now you're able to answer it. Okay, you have 10 minutes. After 10 minutes, I will close it and perhaps then I can have few questions more from the floor. Okay, so it's 11:57. Those who haven't submitted, please do so because else I'll close the link, okay, for response, so you unable to submit anymore. Okay, so please do so as soon as possible right now. $122, not increasing. Yeah, I'll give you another 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 2.5, 2.5, 1.5, 1, 0.5, 0.25. Is that all? Anybody else? Because I want to close. I think we have around 130, right? Happy New Year. Thanks, Nicholas. Happy New Year. Wow, there's a lot of emoji. Okay, so I think there's no more response. So I will end the response, right? Okay. All right. Thank you very much to everyone. Before I wrap up, basically, again, I just want to know, is there any other things that you want to highlight? It can be either for an assignment or perhaps related to the lab test or whatsoever. But I just want to make myself clear that for the assignment, those who already email me, right, I'll already give you your group and the question number. So you have to relate to that group and the question number. And if you receive the email, the first group is the one that I've mentioned, because I think it's a bit confusing when I have another group numbers. Okay, so basically that is the numbering for that specific question. Okay, so you have to refer when I say that your group number is 11, so that is your group number. And then your question, okay, question number 7. Then I've already give you the details of the assigned IP addresses. Okay, so I hope that everything is clear on that. Okay, and the rest I think is also clear. If you click on the link that be given by Dr. Kanan, basically it's already mentioned what is the group that you need to form. Okay, and then the case study already mentioned down here. Case study 1, case study 2, case study 3, except that it doesn't give you the details of the number of employees or hosts. Okay, so the one that I've already email you is the details of it, which are not similar to each and every group will have its own setup. So that is when you need to email me. Okay, then the rest will be communicate later on. Okay, so there are 2 other things. We still have lecture for another 2 weeks, okay, because I have 2 other chapters that I need to cover. And then for the lab, next week will be the last session, okay. Then we will have our test based on the date that's already been given, test 2. And before week 14, I hope that I can finish marking the rest except for the lab or the test 2 itself, okay, and then waiting for the test 2 to be execute, and I will mark it. Okay, again, I will be sorry for those waiting for test 1. I haven't finished marking yet, and I will try to finish up as soon as possible. Any other question? At the tutorial, sir, the tutorial later is 3 p.m. or 5 p.m. Those who have a session with me for Friday, basically you have a session between 3 to 5 p.m. Okay, and for those who supposedly have session with me on Thursday, yesterday, basically because yesterday is a public holiday, so there's a replacement lab. Okay, you can join me after the first session, which is the second session will be 5 to 7 p.m. But if you wanted to join earlier, so you can join 3 to 5. Okay. So I've emailed you for the assignment group, but you haven't updated it yet. Yes, because I've updated it on last Wednesday. If you email after like 8 p.m. Wednesday, then I haven't updated or I haven't replied to it yet. Okay. So you have to wait for me to reply to you so that you're able to start your assignment in details. If don't have assignment group, can I still email you to be assigned in a group? Yes, but it will take some time. It's best if you can form your group yourself. Okay, so to answer Lokman Hakim question, Muhammad Irfan, sir, if my tutorial is on Monday, do I need to join the replacement? What, Monday? There's no replacement. Basically, the replacement for those who on Thursday. But if you haven't, if you miss your own session, yes, you can join either 3 p.m. or 5 p.m. But later on, you have to perhaps email or inform me that you are from other groups because when I flash the QR code, it's just for that specific group. Right? Anything else? Perhaps to start, I can end up the recording.